In this next module, we're going to expand on energy and reactions and systems and whatnot. We're just going to take it past what I've titled thermochemistry, and when we expand it, refer to it as thermodynamics. So we spent a lot of time so far, secretly or overtly, talking about the first law of thermodynamics, which was the conservation of energy law. Now we're going to add in the second law of thermodynamics, which is essentially you can't win or break even in an energy transaction. There's always some kind of tax that you have to pay. So, an example of what I mean by this, if you have a rechargeable battery and it does 100 kilojoules of work before becoming a dead battery, if you want to recharge that battery, it will take greater than 100 kilojoules of energy to recharge it. So, right, we've used 100 kilojoules, and then in order to make the battery capable of delivering 100 kilojoules again, it will cost us more than 100 kilojoules of energy. And you've probably observed or experienced this in just rechargeable batteries get warm when you recharge them. Right? That is extra energy that's lost in the form of thermal energy because of the process that's happening. We will also spend a lot of time determining if a reaction is thermodynamically favorable or spontaneous. I tend to use these two interchangeably. I think the word spontaneous has been used traditionally a lot, but we don't want to confuse that with how quickly something goes. So the trend is to move away from a rate sounding word to thermodynamically favorable. I'm probably going to be really bad at remembering to use thermodynamically favorable, but I'll mention both just to cover my bases, depending on the book that you're following. So if it's favorable or spontaneous, it means that the reaction occurs without ongoing outside intervention. So an example, if you put a book in a gravitational field and let go, it will fall. So if you drop a book in a field, it falls. Like, you don't have to put in outside intervention. You don't have to put in extra effort to make that book fall. Now, the reverse process, taking the book from the ground and picking it up to put it on a desk, you need continuous, ongoing outside effort to put that book back where it was. If something is not thermodynamically favorable or non-spontaneous, it requires outside intervention. Well, I just explained that. So this is what we're talking about when we say favorable or not favorable, spontaneous or non-spontaneous. In general, exothermic reactions, so if you have a delta H less than 0, a negative delta H, you end up with a favorable reaction. Endothermic reactions are generally non-favorable. However, delta H is not the only component, because there are some things that are endothermic but also spontaneous or favorable. So ice above 0 degrees Celsius will melt spontaneously. You would have to put in effort to keep the ice from melting. So ice melts above 0 degrees. Sodium chloride dissolving in water is an endothermic process. Ethanol evaporating, so just alcohol going from a liquid to a gas. These are all endothermic and spontaneous. The thing that is common across these three examples and across any other example that you're going to find that's endothermic and favorable is that there's an increase in the disorder of the system as you go. When ice melts, we have solid particles turning into liquid particles. They're moving faster, they can move around in more space, I mean, similarly with the ethanol, it's liquid particles turning into gas particles. They can move around faster and in more space. Um, Sodium chloride dissolving, you're taking an ionic lattice and splitting it up into individual ions. So, this disorder, the term that we use for it is entropy. So, entropy is a measure of the dispersion of energy in a system. So, more disorder means more entropy. If it is getting messier in any way or more complicated, then the entropy is increasing. So, second law of thermodynamics, for any thermodynamically favorable or spontaneous reaction or process, the entropy of the universe increases. This is a state function, and also a a chemical system proceeds in the direction that increases the entropy of the universe. So, the second law of thermodynamics is essentially everything goes to crap naturally. This is the natural state is that we're moving in a direction that increases the entropy of the universe.